Today, we are going to explore chain fountains from multiple technical angles as we work to resolve an ongoing debate between Steve Mould and Mehdi from ElectroBOOM. A chain fountain is a really cool effect in which a bead chain self-siphons out of a container, and as it picks up velocity, it actually grows upwards against gravity as it's coming out of the container. The Royal Society attempted to explain this, and that's kind of the side that Steve Mould takes, but I believe that Steve Mould, the Royal Society, and Mehdi are actually all wrong in this case. Steve Mould believes the chain fountain grows as a result of a force reaction with the base driving the bead chain upward. Mehdi believes that there is some time constant required for the beads to actually change direction as they go from upward velocity to downward velocity. For a lot more details, you should watch their videos because they do an amazing job of explaining what they think is going on from a technical standpoint. But let's start out this video by explaining the components of a bead fountain. First, you have the upward traveling portion of the fountain that moves against gravity. Then we have the curve where the beads finally turn downward and travel in the direction of gravitational acceleration. The height of the chain fountain is simply the distance from the top of that curvature to the base where the stationary beads lay. The longer this portion is, the higher the tension at the very top of the chain will be because it's having to support more mass. It's also important to note that all portions of the chain in movement are traveling at approximately the same velocity. It's just changing the direction of the velocity vector as it goes around the corner. So the tension at the top portion of the chain is roughly equal to just the mass below it times gravity plus the tension required to accelerate the stationary chain to its current velocity. So again, the higher the chain, the higher the tension will be at this region. That means that something has to create this lifting force to make the chain go higher and higher upwards, or in Steve's case, something has to be driving these beads upward from the base. So if we have to have a reaction off of the base to create a chain fountain, we can just remove the base and see if a chain fountain still presents itself, right? But doing this really isn't that easy because the chain relies on a weight differential in the downward portion to actually drive acceleration and thus velocity. So to get this velocity, we just add a weight, in our case, a copper rod. And this is really cool because even though the weight is higher, the gravitational acceleration stays constant, so my velocity for a given drop height should be identical. And we all know that the chain fountain's height is just a function of velocity. So in the first case, we're going to test just a typical chain fountain with a base and the copper weight included. I've placed a base in here so the chain can react off of something, and the chain gets up to about the 3.5 inch mark, and that was the best case out of 4 tests in a row. Now, when I remove the base, we actually get just over 4 inches. So with no possible way for the chain to react off of anything, we get a higher chain fountain. But let's be honest, that's not really what the Royal Society was getting at because they had specifically mentioned the force reaction to accelerate the rest of the chain, and that doesn't exist in this test case. We would expect this to occur because we know that force is equal to mass times acceleration, so if we have to accelerate mass, we have a higher resistive force. It's very similar to how this string can support this weight if I lift it slowly, but if I accelerate it really quickly, it easily snaps the string. Steve and Mehdi both used a bead chain on the ground to kind of illustrate their points, and I had this awesome test setup ready to help Mehdi prove Steve wrong, but on the very first test run, I crashed it into a curve, and I never got to actually illustrate what I was trying to prove on Mehdi's case. But Mehdi released a video today in the middle of me filming this that actually does what I was going to do anyways, probably in a better context. So there's no need for this anymore. I just blasted a whole bunch of really expensive RC parts for no reason. But using another RC car, I was able to prove that with enough velocity and acceleration, you actually can get a chain fountain to grow higher than its original point when it's laid out, all spaced out horizontally on the ground like Mehdi and Steve are using. You can see because this fountain crosses over the knot in the middle of the wood here. I also made this pretty crazy contraption that allows me to power these rollers at a pretty high RPM, and I'm setting the speed relatively precisely so that I can control exactly what velocity the bead chain's going through it at. And I'm reading the velocity actually with a tachometer that I correlate to linear velocity. And the idea in my mind was I'm going to create some really reproducible chain fountains, and for the most part that worked, but I'm going to explain here in a little bit why I didn't really take it much further. Beads coming out of a container all stacked on top of each other also provide some really chaotic movement, and that's inefficient when you're trying to build a chain fountain. But I was filming this in slow motion to try and understand if the beads are actually acting as a rigid body and pressing against each other as Steve had hypothesized in a prior video. For these chains to transmit any real compression, they either have to be touching each other when they're bent at a sharp angle, or they have to completely collapse on themselves because the little cylindrical portion in the middle actually slides in and out of the bead itself. I couldn't find any clear-cut example of this compression actually occurring as the bead chains accelerate, but I don't think this was a super conclusive test. Either way, I'll say there's really not any evidence I could find that supported the idea that compression is occurring in this chain. Now, I want to clearly state that I'm not saying no reaction force does occur with the base. I actually think a force does occur because that's how rotational inertia works. However, what I am saying is that I don't think that force is necessary for a chain fountain to grow at all. The base of the container is only necessary to support the mass of the beads that are sitting there stationary. Now, let's talk about why I think Mehdi is incorrect. The radius of curvature at the top of a chain fountain is very inconsistent. But Mehdi also claimed that this is a function of some time constant. But if we don't see the radius of curvature at the top of a chain fountain increasing with velocity, time is not constant. So the idea of a time constant doesn't really exist in my mind. Now let's talk about what I think is going on, and we're going to start this off by observing what the end of a chain fountain looks like. The beads are rotating around a common point for the most part until the end. That's when the beads all fling outward. I believe this flinging action is similar to spinning a ball around and feeling the string it's attached to pull against your hand. The tension in the string I'm spinning is centripetal force, and I believe the beads in a bead chain are experiencing a reactive centrifugal force in the radial direction. And these beads, as the velocity increases, are trying to fling outwards from the center harder and harder, but it's the chain tension alone that is keeping this radius of curvature from flinging completely outwards or completely upwards. This tension on both sides of the chain is what's required to keep the system balanced. We can quantify the centripetal force as being equal to that of mass times velocity squared, divided by the radius of curvature. And bead chains are kind of unique in that they have a relatively high minimum bend radius for how flexible they are, especially under tension. So the faster the beads travel, the higher the centripetal force. And then it finally dawned on me after spending way too much time on a bunch of random tests that you can never truly remove 100% of any lever effect because of things like inertia and friction. So these tests will never prove anything. And you also can't prove that it's necessary because that's going to take some really expensive instrumentation and a ton of testing that just has, no real benefit commercially or to even life that I can think of. So who would do that? And we already know that this is a very chaotic process in nature, so it's really hard to get any accurate data. Which led me down the path of, well, let's go back to the math and let me approach it from a clean slate of how I think I would calculate it if it is centripetal force that's driving this. So if we break this down, we have an increase in tension here from the reactive centrifugal force pushing all these beads outwards as they spin around. And then we have a force increase here where we accelerate from 0 meters per second here up to our actual velocity here. We're going to call this distance S, and that'll become important. Now, we're going to start out by looking at 90-degree sections for two key reasons. The first is because these masses cancel out since it's the same number of beads, but the second is because the center of gravity pretty much falls exactly on the radius. So that means we can use them interchangeably. And so our centripetal force acting out this way, since our center of gravity is here, is equal to mass times velocity squared over radius. And the radius is this distance right here, which pretty much falls in line with our minimum tensile bending radius. We can also visualize this as the minimum distance traveled to go from the horizontal position to the vertical. And so the tension increase at these spots from the centripetal force is just this divided by 2 because it's held by each side. Now we need to know the force here to see if this is increasing faster than this force. And remember, this force is just equal to force equals mass times acceleration. But we know the masses cancel out. What we don't know is what this acceleration is, but we do know our distance s. And s is equal to our radius times 2 times pi divided by 4. This is the circumference, and this is just 1/4 of a circle. And when starting from 0, acceleration is equal to velocity squared divided by 2s. So we can basically plug these in together to get acceleration equals velocity squared divided by 2 times radius times 2 times pi over 4. And all this cancels out. So acceleration just equals velocity squared divided by radius times pi. So to summarize that with a much cleaner equation sheet, we're taking the centripetal force for a 90-degree bend is equal to mass times velocity squared divided by radius. Tension is equal to only half that because there are 2 legs to our chain fountain. Acceleration in the linear portion is mass times acceleration, and the distance traveled throughout this linear portion is equal to the circumference divided by 4. Now to find our acceleration from 0 velocity, we just take velocity squared divided by 2s, which gives us velocity squared divided by the radius times pi. So the force here from linear acceleration is equal to mass times velocity squared divided by radius times pi. We see that mass times velocity squared over 2 times radius does not equal mass times velocity squared over radius times pi. So then we could plot out these two forces relative to each other, and you can see that they do diverge. The centripetal force is increasing faster than the force from linear acceleration, which means we should see chain growth. Now, for me to calculate the actual amount of chain growth, I have to take an entire 180-degree section, which requires me to understand where the new center of gravity falls, but at least I know that I'm doubling my mass. So the tension from centripetal force at 180 degrees is 1/2 of my original centripetal force calculation times twice the mass, but I'm going to scale for the center of gravity position from the radius. And this way, I don't have to recalculate everything. It scales linearly. Now, my chain height increases as a function of the tension from 180 degrees of centripetal force minus my force from linear acceleration. It's this force here minus this force here divided by the mass per meter times gravity. And I plotted this out right here to approximate how much the chain would grow. And even better than that, the Royal Society has empirical data that correlates the chain fountain height with the drop test height. I can take that drop test height and scale it for velocity based on gravitational acceleration. And it gives you this curve that shows that chain height does grow quadratically with velocity. Even better, these two curves are remarkably close to each other based on measured data as well as my calculated data, except they do diverge at the higher velocities. But one thing I should note that their own curve fit that I'm using diverges from their own test data at higher velocities. If we take one single data point above a certain crossover velocity, we see that I am closer to predicting their height than their curve fit does. This may also help to explain why chains like plastic beads that can easily double over on themselves have a lot of trouble exhibiting a chain fountain. You see, because if they fold in half, their mass is almost centered on the center of rotation, which means there are situations where you never have an upward component of centripetal force. You only have an outward component, and that's not going to drive an increase in height. As an example, the chain of levers that Steve had mentioned that didn't actually work that well could double over on itself, even though according to their explanation, it should have worked better. But I think what we're seeing is that that mass is not able to act upward that well against the center of rotation. I bet if they were able to limit the bend radius of that chain and maybe make the levers a little smaller, you would see that it actually does start to grow. And again, that's because you can have mass above the center of rotation, which is what drives that upward centripetal force instead of just an outward force. But didn't the Royal Society prove that centripetal force cancels out? They had that whole thing where the force required to accelerate the stationary beads was equal to that of the centripetal force, right? And this is where I'm kind of confused as to what they were trying to say, because they used the term momentum, and then mass times velocity squared, and a few things that didn't really characterize a force at all. Momentum is not a force. Another important thing to note, the actual bend radius isn't necessarily critical, it just really helps us that we have a minimum bend radius under tension to start with. You see, because if you extend the radius for, say, the stationary to the upward traveling portion, all that means is your S variable goes up, which increases your mass, but it decreases your acceleration proportionally, so the answer is the exact same. Now let's say the top of the curve actually does expand with velocity, such that the time to travel around that curve is always constant. But Mehdi has a point. But what's causing the chain fountain, in my mind, is the difference between centripetal force and the force to accelerate the stationary pieces. Now you can come to the exact same conclusion with rotational acceleration. Starting out with our same 90-degree segment, we are going to derive angular acceleration from our angular velocity, and we can convert that to linear velocity and radius. So then we get our acceleration in terms of velocity squared divided by r squared times 2 theta. And theta is just pi over 2 because it's 90 degrees, which means acceleration is velocity squared divided by radius squared times pi. Now, the rotational inertia of this segment is just mass times radius squared. And we're using the same center of gravity position and mass for that segment as previously. We know that the torque to rotate this segment up to speed is equal to the rotational inertia times angular acceleration, but we can also take this torque and calculate the force required at the radius, which gives us mass times velocity squared divided by r times pi. And that gives us the exact same answer as previously using linear acceleration, which means we're going to get the exact same results. Now, as long as the tension from centripetal force is greater than the force to accelerate the stationary links, we should grow. And I propose that the ratio between those two should be known as the Mould-Mehdi ratio. And as long as the Mould-Mehdi ratio is greater than 1, we should see a chain fountain that grows. And then we have the coefficient for our chain height growth curve that explains how this grows is a function of velocity, and I propose we call that coefficient the Mehdi coefficient. And one more thing, I'll be honest, I kind of just glazed over the last portion of the paper because I got through the first portion where I didn't totally agree with how they were canceling out centripetal force, so that's when I started to pick up my own math and do it myself. It's possible they're saying something that I'm not understanding on the first quick reading of it, so please let me know. And the very last note I want to make about this is that a block shot from the edge definitely does not travel substantially higher than a block shot from the center unless if there's a really big difference in how that energy is transferred. As a matter of fact, the argument's always been it's amazing that a block shot from the edge even travels as high as one shot from the center. To see all the math and discussion on this, Veritasium did a very great video on this, and there's loads of content on YouTube. So overall, we've seen that technically you can create a chain fountain without a base at all, though that kind of ignores what the Royal Society was trying to say, about the force balance between centripetal and the force required to accelerate. I even went through in detail what I believe is the math that's going on here. I should point out though that I don't think it's that exact when it's coming out of a container because, like I said, it's real chaotic flow, so it's not nearly as efficient as my equations would predict. The interaction is really complex. It's an insanely difficult problem to properly analyze and simulate because so many different situations can occur as this thing comes out of the container. And in saying all that, I'm sure there are loads of assumptions that I've made that are incorrect. So let me know, do you think the Royal Society did miss those key components in the denominator, or is there something I wasn't understanding about the acceleration side that go on when the bead chain happens? Steve and Mehdi have both done a great job at providing some really convincing arguments and making this kind of an open discussion, so I do look forward to seeing what everyone thinks is actually happening here. Please leave a comment letting me know, who do you think's right, what do you think's going on, and is this something entirely separate creating all this that maybe no one's thinking of? Thanks for watching, and I look forward to hearing what everyone has to say about this.